This is lesson 1.3 in geometry. So the big idea is that points and lines in discrete geometry and in graph theory have different properties than points and lines in Euclidean geometry. So in the first two lessons so far that we've covered in the geometry book, we've been talking about what's called Euclidean geometry, named after the person who pretty much came up with it. So we've talked about two specific ones. We haven't really focused on what they're called in terms of identifying and classifying them. Today we're going to do a little more of that. But we can kind of wrap both of them into the same category of Euclidean geometry. So there's synthetic Euclidean geometry and there's Euclidean plane geometry. It gets a little wordy, and I don't want to get too hung up on any of that, but um, we do want to look at the difference between those two, slight difference, and then we're going to look at two other types of geometry. The whole point of this is to understand that there are different categories of geometry. We mainly focus in this coursework on Euclidean geometry, but it's important to understand that depending on how we classify or the properties of the most simple things in these curriculums, basically, the points in the line, if we look at those differently, if we classify those a little bit differently, and they have different properties, they kind of give us these different types of geometry. And again, we're mostly going to focus on Euclidean geometry, but today we're going to just kind of like a bird's eye view of discrete geometry and graph theory. So going back to Euclidean geometry, what we've covered in 1.1 and 1.2, and basically everything that you've covered before in pre-algebra and anything leading up to this, we're looking at points that are representing a location. When we're looking at plane geometry, those points are actually given a specific ordered pair, the x comma y. In synthetic geometry, they're not given that exact location on a graph, but they do represent a location. And then a line is when you put all these points together and you connect them in the shortest path possible, because you're not taking any extra detours, just shortest path between 2 points is a line. And then if we actually are looking at the plane geometry, we're on a graph, we're on a coordinate plane, and so lines are sets of ordered pairs. We've got all these ordered pairs and they are connected. So that's Euclidean geometry. That's what we've been talking about, just not maybe going and focusing too much on that word itself. Now, discrete geometry, again, we're going to go ahead and just look at the most simple parts of these to show how they're different. So points and lines. So in discrete geometry, a point is just a dot. It's just a dot. It does actually take up some space too. So up here, we just talked about points don't actually represent a size. They don't have necessarily a length or a width or a depth. But here, a point is going to be a dot and it has size. The way to think about it, if you take a picture on, let's say, a phone that's a couple years old and you zoom in, it gets very pixelated and you can see those pixels. And a better camera has more pixels. So when you zoom in, they're smaller. And then as you zoom out, you get a better picture. So a pixel is kind of like a point, it's a dot. It's a tiny dot that makes up a picture. So it's a good way to think about it. All of those pixels sitting next to each other are kind of like points in discrete geometry. And then a line is a set of dots in a row, but we don't actually connect them. So discrete geometry is just looking at dots, basically. So let's kind of look at a couple different situations here. If we have Euclidean geometry and we have two lines that cross, they look like this. And you're going to want to copy this down. All right, and they have this point where they intersect, and that is a common point to both lines. Now in discrete geometry, you've got a point being a dot, and a line is a set of dots. And so it looks like this, but they're not connected. There's space between them. And so we can draw two intersecting lines in discrete geometry, and they may or may not intersect. So let's see what that looks like. I can draw two of these crossing like this, and sharing a dot. So I'm going to make this line that's going this way share that middle dot. And so they have what's called a common point. So these two lines intersect and have a common point. But in discrete geometry, we could draw two lines that cross that don't have a common point. So if we draw this line, think about how can we draw a line that intersects this, but they don't have a common point. So they're not going to cross right on this point. They're going to cross basically in between points. So these are two discrete lines meaning made up of dots and they're not connected, that do not have a common point. No common point. And that's basically all we're going to touch on in discrete geometry. Depending on where you go with your studies, there are some places where discrete geometry will be a very big part of the curriculum. But here we're just touching on it, and we're going to spend most of our time today on graph theory. So in graph theory, first of all, there's a couple of vocabulary words that we're going to use a lot that we're not used to using all the time, and so we want to focus on those. You can see those here are in bold and capitalized. And so we're going to focus on those first, and then we're going to talk about these as networks being traversable or not traversable, and how can we identify those. So graph theory, again, we're going to break it down to the simplest things that we talk about in geometry, a point and a line. In graph theory, a point is called a node, and we're going to use that word a lot. It is part of a network. So if you look at all of these would be networks. A line is called an arc. And you've probably used that word before. An arc you probably automatically think of as something that's curved. So clearly this does not need to be straight. These would be considered arcs. Okay, and there are lines that connect the nodes. They do not need to be straight. They can be curved, they can be straight. They're not defined by that. And so they connect two nodes. So like this arc right here connects node Q and node R, but they can also just connect a node to itself. You have this point right here called a node, and it's identified as N, and it has one single arc that connects to itself. All right, so here's three examples of networks. The dots are the points are called nodes, and then the lines that connect these are called arcs. And so what we're going to look at on these specifically is if they are traversable or not traversable. There we go. That's a better focus for you. And so if it is traversable, it means you can trace over all of the arcs in this network exactly once without lifting your pencil. So that would be true here, right? I can trace this whole thing without lifting my pencil. Right here, I can trace the entire thing. I will hit the nodes more than once, but each arc, the lines, I will not reuse it more than once. And over here, we won't go through the whole thing, but you have to really think hard. How do I kind of go through this whole map or this whole network without going over an arc or a line twice? If I can't, then it's not traversable. If I can go through the whole thing, then it is traversable. And that's what we're going to spend most of our time on. So one, looking at it and seeing if we can figure it out, and then also being even more specific and finding some keys where we don't have to simply trace. We can identify some properties of these networks that will help let us know if it's traversable or not. All right, so we're going to talk about these, again, these are the nodes, the points, as even nodes or odd nodes based on the number of arcs meeting at a node. How many arcs are meeting at each node? And then we'll get to this key in a second. Let's come back to this. So right here first, we're going to talk about how many arcs are at each node in the networks that are pictured here. So we're going to go through each point or each node and figure out how many arcs are connecting in that spot. And then based on the number of arcs that we have there, we'll either call this even or odd. So starting with n, and this one can be a little tricky. You might want to say 2 because you've got the line coming out and the line coming in, but it is one single line. Okay, so there is just one arc there, and that would then be considered odd. That's a very specific case. We're not going to look too much at those. We're going to be looking at where we have multiple nodes creating a network. So when we look at O, I've got this arc that meets at node O, I've got this arc that meets there, and I've got this arc that meets there. So O has 3, so it's odd. And P has the same 3 arcs that connect to it as well. So that has 3. So that's odd. Here's Q. It's got this one, and this one. So Q has 3, and that's odd. R, 1, 2, 3 lines meeting at that point. 3 arcs meeting at that node. So that's 3. So it's odd. S is also 3. And so it's odd. And T is also 3. And so it's odd. So let's go back to these for a second and talk about if they're traversable or not. This first one is traversable. I can start here at N, and I can trace the entire network without overlapping any arcs. So this is traversable. This one I can start at O, and I can go all the way across. I can go all the way across, and then I can go here. So I can trace the entire network without overlapping any arcs. This one you can try starting in a bunch of different spots. But if I do this and then down, start thinking ahead, I can go over. Then if I go this way, I've already done these. If I go this way, okay, that might be a possibility, right? If I go all the way around, I can't go this way because then I'm stuck. I would have to overlap these. So I could go down. I can't go across. I've already done that. I can go this way, but again, now I'm stuck and I haven't been able to trace this. And so this is not traversable. I cannot trace all of the arcs exactly once without lifting my pen or my pencil. We're going to come back to this point over here in just a second. Let's turn over to the back. Are these networks traversable? If yes, use an arrow to show the path. And so you might start out here and go here, 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 here. Okay, it seems like I kind of got lucky there. That worked. What if I started here? I could go 1, 2, 3. At this point, I've got to go out this way or this way or this way. So this one may, depending on where you start, may not look traversable. Just because you started at A and it didn't work doesn't mean you can't start somewhere else. So what if I started at C? I go here, here, here. That's not going to work. What if I started at E? Think about it. The last thing I got to do is go this way because I'm stuck once I'm out there. So can I go all the way around and end up back here? This way, maybe up and over. Now I can't go both ways. So what if I went this way, here? Nope, that's not going to work. But again, when we started with D, we could go this way, here, 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 here. Remember, you don't have to end up back where you started. You just have to cover all of it. So that would work. What if I started at B, up, over, here, 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 and then back out? That would work. So this is yes, traversable, and then use arrows to show your path. So let's start at B. I could go this way, and then this way. I could go this way. Here, again, I'm allowed to hit this point again. I just can't go over a line or an arc that I've already done. And then I would go this way, and then I would go this way. So that one's a yes, that one works. Okay, on to the next one. If I start at F, let's say I go here, 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 here. I can get all the way around. This is a yes. Show my arrows this way, here, 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 and here. And then the last one, let's say I started at K, work my way around this way. And if I'm looking ahead, I start to see a problem. If I go up here, all right, I'm gonna go here, here, here. I never hit the bottom. So what if I went around and I covered the bottom, went up this way, down, and now I gotta go one way or the other, and that's not gonna make it. Started a different letter. What if I started at L, up, over? Okay, I'm gonna end up crossing. If I go down, so let's say I went up, here, 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 and crossed. All right, I still didn't hit this. This one is no, this is not traversable. And you might say, what's the point of this, right? And so in the book, it talks about this city that had a bunch of bridges connecting all these islands. And the original problem where this came from was discussing, could you come up with a path where you go over all of these bridges just once? So pretend that all of these dots are little islands, and these are bridges connecting all of the islands. Is there a path where you could walk the whole network and just go over each bridge one time? You may end up back on the same island, but you've only crossed each bridge one time, and then you maybe end up back where you started, or maybe not. Over here, this would not work. Now, after a while, it kind of gets a little cumbersome to sit there and try all these different paths, trial and error, trial and error. So mathematically, we like to come up with ways of figuring this out without just doing trial and error. And so if we go back now to the front, here's the key now that we're going to talk about. A traversable network can have no more than 2 odd nodes. So it can have 1 odd node, it can have 2 odd nodes. But if it has more than 2 odd nodes, it's not going to be traversable. And here's why. An odd node must be the starting point or finishing point of a traversable network. Let's read that again. An odd node must be the starting point or the finishing point of a traversable network. Okay, must be. Think about why. If you have an arc and a node and it just has 2 arcs, one comes in, one goes out. Okay, that doesn't have to be the starting point or end point. It just goes through it. But if I have 3, right, and let's say this came in and went out, it's going to have to come back. And when it comes back, there's nowhere for it to go. Or if you started with this, you go out, you go all over the network, and you come back, right, and then it can go out somewhere else. So it could be the starting point, and I could find my way around and go through it again. Or it could be the end point, right? I went out, and then it comes back there. So we need to focus on how many odd nodes there are here. If there's more than 2, it's a clue to us that this is not traversable. So kind of going back to these ones, this had 2 odd nodes. O and P both had 3 arcs. And we found that this was traversable. So it's okay for 2 of them to be odd. Now if we go over here, Q, R, S, and T, all of those were odd. All of those had 3. Now remember, it's not just more than 2. Like if all of a sudden one of these had 4, that's now an even one, and that changes things. If it's even, there's ways to get back to it and continue going around. But if it's odd, you run out of ways to go. So once you've gone through it and you come back to it, you're stuck. All right, so we're just looking at even and odd, not 2 or 3, These can get very complicated. It's just even or odd. So let's take that now and go back to the ones we just looked at. If we go back to these ones, let's start here. Why did this one not work? So this one right here has 3. This one right here has 3. So right away, if there's another one that's odd, this is not going to work. Well, this one has 3. This one has 3. This one has only 2. But there are more than 2 points, more than 2 nodes that are odd. And so that's why this doesn't work. Over here, we've got 2, 2. This one is 4, 2, and 2. These are all even, and that's why it works. Over here, this one has 1. This one has 4. This one has 2. Here's an odd one, 3. And this one is 2. So there are 2 odds, the D and the B. And if you remember, as we were trying to go through this with trial and error, when we started at A, we couldn't get it to work. When we started at C, we couldn't get it to work. But when we started at D, there was a way to get around it. When we started at B, there was a way to get around it. And when we started at B, think about where we finished at D. So when you have those odd nodes, it has to be the starting point or it has to be the finishing point. Okay, this one was all even, so that's just a different scenario. But when you have an odd node, we talked about it right here, an odd node must be the starting point or finishing point if it is traversable. If you've got more than 2 odds, it's not going to be traversable. And so right here, we could have, now that we know that information, come up with the answer here a lot quicker based on the fact now that we know that this is odd and this is odd, that has to be your starting point and this has to be your finishing point, one way or the other. So now, again, that could have been a little confusing. Let's go ahead and retry this now, just looking at odds and evens. All right, so right here we have 2. It's got 2 arcs coming into it. This one has 2. J here has 3, so that's odd. Those are evens. F here has 3. So that's odd. And then K has 2. So just looking at that one, it only has 2 odd nodes, which means this could be traversable. And we know that we're going to have to start and finish at those odd ones. So let's take a look at this one. I could go this way, this way, this way, and go boom, boom, boom. I started at J, I ended at F. So this is traversable. And it has 2 odd nodes, so that's why it works. How about number 2? O here is an odd node, it has 3 arcs. N here is an odd node, has 3. M has 3. We could stop right now. It already has more than 2 odd nodes. Here's another one, 3. And P is even, P has 4. But I count these up, I've got 4 odd nodes. This is not traversable. Why? Because it has more than 2 odd nodes. So I don't have to sit there for trial and error and go over and over and over and over and try and find my way around. You could go ahead and try, but you're going to end up tracing all of it except one. You're going to leave something out. It's not going to work. You're not going to be able to go around without overlapping something. And we can start to identify that now by how many odd nodes there are. So then the last one, U has 2 arcs, R has 3, so there's 1 odd. S only has 2, and T has 3, so it's odd. So we only have 2 odd nodes, so this should be traversable. And if you were going to label your way around by like putting the letters in order, you know you have to start with the T or start with the R. The odd nodes are going to be your starting point and then also your ending point. So if I started here, I could go T, S, R, T, U, R and make it around. Notice I ended at R and I started at T. I could do the same thing here, but I don't need to trial and error. I know this is traversable only to odd nodes. So in today's work, you're going to practice creating these and also just looking at ones that are already made, figuring out how many odd nodes there are. Is it traversable? Is it not? Again, this is what graph theory is all about.